All right, I'm back. All right, here we go. Let's finish this up. Chapter 34, Part 2. Okay, so we're going to talk about liquid metal embrittlement. So really, this is not metal right here. This can be glass. This can be different types of material that solidifies within our weld. Okay, ultimately, it's two materials that aren't jiving together. They may have changed in a molecular process, and in that, it's just not mixing together and it makes a crack. All right, porosity. There's two types of porosity. Can you guys tell me? Surface and subsurface. Okay, surface porosity is going to be circular. Subsurface, usually we call it wormholes. It looks like little wormies coming out. Okay, ultimately, porosity is because of gas entrapment. Okay, what do we mean by gas entrapment? Well, we're getting oxygen and nitrogen into our weld, whether we're not shielding it correctly, whether we're long arcing or we have dirty material, it's still creating a gas and it's trying to come out of my weld. All right, so how to prevent porosity? Excessive hydrogen, nitrogen, or oxygen. Use low hydrogen. Use filler metals that have deoxidizers, or turn up your shielding gas. High solidification rate. It means that your weld is becoming hard quickly. Okay, so we may need to preheat or post-heat. Dirty base metal, dirty filler wire. Make sure you clean it. Improper arc length, welding current, or electrode manipulation. All of those can affect it. Zinc from galvanized steel or brass can also cause it. Okay, so we want to make sure that we take out that stuff. We can also grind it out. Excessive moisture. Make sure you bake your stuff. Make sure you preheat the base metal. High sulfur base metal. Well, use electrodes that have better slag, heavier slag that will take it longer to cool off. All right, slag inclusions. What is it? Well, it's whether we have pieces of slag in our weld, right? Usually near the edge, between passes, either way. Too much, not good, okay? So how do we combat that? We clean between the passes better, okay? Other ones, oxide inclusion. What's an oxide? Well, we know that oxides can be rust, but oxides can also be on aluminum and titanium and alloys like that. It helps them not to rust. So if we don't take off the oxides correctly or enough, it will get stuck into our material. So the good example is that usually aluminum melts about 1600 degrees or thereabouts. Okay, when we're talking about oxides, oxides melt usually around a 3000 degree. Well, what happens? Well, what really happens is that we try to do our nice pretty weld, and the oxides sink into our weld, creating an inclusion because they don't melt. Tungsten inclusion. Tungsten inclusion. Well, this normally happens when we're using tungsten, normally in TIG. And what happens is that maybe you've touched it to the material and a little piece stays in our weld. Okay? All right. Incomplete fusion or lack of fusion between adjacent weld passes or the base metal. This isn't good, guys. Okay? This is why I tell you it's really important to pay attention to bead sequencing, how you lay down your beads, because we need to make sure that everything is touching, right? If we look at it, look, okay? We weren't able to hit the edges here. We didn't hit this here, okay? Or when we're doing fillet welds, and usually this will happen more often in TIG, this is called bridging, okay? And we weren't able to sufficiently get into the root of the joint, okay? If we're having incomplete fusion, we need to pay attention and make sure we turn up the heat, okay? Make sure we're using the correct size electrode, and we have good joint design, okay? Maybe our root is too small and we're not able to get in there, or maybe we're using an incorrect position. The other one is weld metal running ahead of the arc, okay? What happens is maybe it gets a little too hot and you're letting that weld metal get ahead of you, but instead of it melting everything, because we're not heating that base metal, it's just kind of sitting on top. Okay? Trapped oxides or slag on the weld group. Well, if we don't clean it very well, it's not going to be able to penetrate. All right, onwards. Incomplete penetration. Usually this is because of what? Improper joint design, improper electrode selection, right? If I'm not able to get into my joint, I have too big of an electrode, I'm not going to be able to get into my joint correctly. If it said to back gouge and I did not back gouge, I may have this little void here on the other side because I didn't back gouge before I put that other pass in. Okay? So, how do we fix that? Excessively thick root face or insufficient root opening? Make sure you pay attention to your joint fit up. Insufficient heat, well, turn it up. Slag ahead of the arc. Make sure you pay attention to your work position and your angle. Electrode diameter too large, you can't get in there. Either make your root opening bigger or use a smaller electrode. Misalignment. Well, sometimes it's hard to prevent that, but maybe you need to pay attention to what you're doing and back gouge it. Or failure to back gouge. Make sure you pay attention to your procedures. And bridging of the root opening. Maybe you need a bigger root opening. Maybe you need a smaller electrode. Undercut. All right, everybody's done it. Undercut. Those little sharp bites. Why does this happen? Well, we know what makes a good weld and what makes a bad weld. When we get undercut, it's usually because of what? Angle, arc length, amperage, manipulation. Any of those things can cause what? Undercut. We're actually cutting into our base metal and we're not leaving anything in there. Okay, this can also be because we're moving too quickly. More likely, undercut happens when we're going vertical up. All right, overlap. This is that belly going over the edge of my material, right? It means I don't have any complete fusion. And I can create a stress here, right? Right here, I probably get a toe crack. All right, excessive reinforcement. That can be on the root. That can also be on the face. If I'm doing an open root, how much can I have that hangs past my material? You should only be able to have a 1/16 that hangs past your root of reinforcement. Now, if I'm doing a test plate according to AWS D1.1, what would be the maximum reinforcement that I can have on my face? The maximum reinforcement for AWS D1.1 is 1/8 of an inch. That means from the base metal to the crown, it can only be 1/8 of an inch. If it's more, it's considered excessive. Now, what about the edges? Okay, the edges, I can have a 1/16 hangover on both sides. If it's more than that, it can be considered excessive. Underfill. Okay, guys, underfill is caused by poor bead placement. Maybe you decided to, fill in the edge here and fill in the edge here, and then you're like, I'm going to hit it right here. But what really happens is that I have underfill, so I'm going to put another pass here. And ultimately, then it makes it excessive. Okay, so planning ahead is really important. Arc strike. Hey guys, this is it. As an inspector, this is my biggest pet peeve. I can't stand it. Okay? What happens with an arc strike? Well, really, you should always be striking where you're welding. Yeah, it happens. I get it. But let's remember something, okay? Let me show you. All right, so maybe I arc striked right here. Well, I want you guys to remember that all along this area that you arc struck, you also changed the molecular structure of your material. You created a HAZ in an area that shouldn't have one. And in that case, then you're going to cause different loads and failures. So what do you do when you get an arc strike? Well, if it's on a test, you got to ask, because sometimes arc strikes are plans for failure. Okay? But in the field, you turn around, somebody calls your name, hey, well, shoot. Okay? So you take it and you need to grind it to sound material. Okay? Easy fix. Spatter. Spatter is ugly. Okay? Pretty much, what does it tell me? Well, I probably have a long arc length, but we also know that certain rods are going to spatter a little bit more than others, okay? If you get spatter and you remove it, cool. All right, points to remember. Discontinuities are classified as defects when they exceed the minimum requirements permitted by the controlling coder standard. Weld stresses can be concentrated or enhanced by discontinuities, leading to failure under load. Cracks are fracture-type discontinuities and are not permitted in most codes and standards. Remember, the higher the carbon content of the steel, the higher risk of cracking, right? Payoff with high steel or high strength steel and high carbon steel is carbon, strong, but payoff is what? Brittleness. So it pays attention, it's important for you to preheat, post-heat, and pay attention to your inner pass temperatures. Okay? Cracks. They're classified according to the orientation on the weld. Inclusion. Inclusion means it's in it, okay, and it's a foreign matter, right? It can be base metal, filler metal, or non-consumable electrode. Incomplete fusion and incomplete penetration are found in areas with incomplete melting between the base metal and the weld metal. Excuse me. Incomplete fusion is less desirable than incomplete penetration, meaning incomplete fusion didn't fuse the edges. Incomplete penetration means you just didn't get it there. Okay? Incorrect shapes like undercut, overlap, excessive reinforcement, underfill, concavity of your root surface, melt through are all unacceptable weld profiles. Arc strikes, they degrade base metal properties, especially on hardenable steels like medium and high carbon steel, or even alloy steels, and they create a brittle martensites, that's the changing of your grain structure, and create like a rapid quenching effect on that high temperature. All right, guys, as always, have fun.